Hello everyone. Let's solve some of the linear algebra questions that are asked in the GATE exam in the previous year. So let's start with the question number 1. Question 1 says A is a square matrix is called a singular if it's okay. Recall when we call any matrix is a singular if we got the determinant of any matrix, let's say here it is A equal to 0, then we can say the matrix A is a singular because we got the determinant equal to 0 and it is the definition of this singular matrix. So we can select the option B because the if any matrix is singular then the determinant must be 0, or in the vice versa if the determinant is 0 then any matrix is singular. So the statement B is the correct one. Okay, now let's move to the question number 2. Question 2 says the eigenvector of a matrix. Okay, we have a 2 cross 2 matrix. Now they are asking about the eigenvectors. So we can go by usual process, which is just find the eigenvalues. Let's call lambda 1 and lambda 2 and this and that, and then we have to just compare this ax equal to lambda, and we have to find the this vector x by solving the equation that we get by using this first time lambda 1 and second time lambda 2, but it is very long process. So just simply what we are going to do, we are going through the option. So now if any vector is an eigenvector, then this condition ax is equal to lambda x must be satisfied. Then and then we can say the this vector is the eigenvector of this matrix A, and lambda is the eigenvalue corresponding to this eigenvector. So now we have given the matrix A. So let's write it here. We have given it 3 minus 1 and 3. Now we have to find which one of the these four options contain the two eigenvector. So first of all, let's start with the option A. So let's check for this 1 1 vector. So let's write it here. So now we have to do the multiplication and look what we get. Just 3 minus 1. So here we got 2. Now here minus 1 plus 3. Okay, so again we got 2. Now we can take 2 out from this matrix to make in the form of this lambda into x. Here x is our the initial matrix, which is 1 1. So if we want to represent this matrix in this form lambda x, then we have to take 2 out. So let's write it outside. So now you can see we are getting the same vector here, and here we got some scalar. It is exactly same as this equation ax. Here the matrix is A here. Now this is the eigenvector x, and here we get lambda times x. So this condition is satisfied by this 1 1 vector. So it is clear that one of the eigenvector of this 2 cross 2 matrix must be 1 1. So now let's look at option B also contain this 1 1. So now let check this as either the this 1 minus 1 or minus 1 is the other eigenvector. So now again write this matrix A as it is. Now let check this option this matrix sorry this vector first 1 minus 1. So let write it here 1 and minus 1. Now we have to do the multiplication. So what we are getting here, just simply 4, because these 3 multiply with 1, so 3, and minus 1 with multiply with minus 1, so again 1. So 3 plus 1 4, and here we are getting minus 4. So now you can see to make this vector in this lambda into x. So here x is this vector, which is simply just 1 minus 1. So let write here we have x equal to 1 minus 1, and now we have take out this 4, then and then we get here 1 minus 1. So again we compare with this ax equal to lambda x form, and we can say this equation again is satisfied by this vector. So we can say that another eigenvector for this 2 cross 2 matrix is 1 comma minus 1. Now for the clarity, you can check this minus 1 vector. It wouldn't satisfy this condition. Let do it here. So let write here this matrix A. Now we have to check for this minus 1 vector. So let write it here, and now let's do the multiplication. So what we are getting here, minus 3 plus 1, so we got minus 2. Now here what we got, plus 1. Now here in the last element here we are getting plus 1 minus 3, so we got minus 2. So now let's make this vector in this form. So it is just simply minus 2 times. Now here it is again satisfying this condition. Then how this both two options are correct? It is not the case, because look at uh, one vector is 1 1, here this 1 1, and we have to find the two distinct vector. So here this vector, it is just simply the negative of this one first. Look here, then it is the same eigenvector, this one, and it is the same one, because we have just multiplied this minus 1, and we know that if any AB is an eigenvector, then KAB is also eigenvector, but it is the corresponding to the same eigenvalue. So we cannot say it is a two distinct eigenvector, because it is just a scalar multiple of this first one. So we can say this one and this last and this first one are just the same eigenvector, but multiplied with a minus sign. So we cannot say these two are they are eigenvector of this matrix, but they are not corresponding to the distinct eigenvalue. So we can say only the option A is the correct one, because now here in the option A we cannot multiply any number to this vector and we get this one, because here the 1 and minus 1. So here we have 1 1, so they are the distinct eigenvector. So we can say that the option A is the correct one. Now you can also check for option C and D. They couldn't satisfy this condition. Ax is equal to lambda x. Here it is the rare case such that these two vectors are just same as this first one, just simply multiplied with minus 1. So we have to choose the option A, because it is the correct set of eigenvectors. They are asking about the two different eigenvectors. So we have to select the option A. Okay, now let's solve question number 3. Question 3 says, if A and B are the two matrices and if AB exists, then what condition must A and B satisfy such that BA also exists? So here it is given that A and B exist. So let's assume any general order for this matrix A. Let's call it A, and let assume it has a dimension of n cross m. And now we have to multiply this A matrix with B matrix. Let's also assume the dimension of B. Now it is given that AB exists. So here the B here vector matrix B has m rows to exist this AB multiplication. And here the here and let's call it P. Now you can see AB exists, because this condition is satisfied. The number of column in the second matrix is exactly same as number of row in the second matrix. So we can say AB exists, and it has an order of this n cross P. It has an order of n cross P. So now we have to find the condition such that BA also exists. So what? So let's write now B first. Let's write its dimension as it is, m cross P, and let's write A here, and it has a dimension of n cross m. Now we want to find BA. Now if this n and P are exactly same, if this n and p are the same, then and then we can say the multiplication of these two matrix B and A is possible. So we can say that the number of column in the B matrix is the exactly same as number of row in the A matrix, because here n represent number of rows and p number represent number of column of this matrix A and B respectively. So we got the answer for the condition such that uh, BA multi BA also exists for this A and B matrix. So look at the option. Option A says only if A and B are the square matrices. Now it is not the condition. If A and B are the square matrices, let's say it is an n cross n matrix. Now here A and B. Now to find the multiplication of AB, this B must has n cross A, and if this is the case, then BA is also exist. But now it is not always case, because it is written only if. So now prove this statement is wrong. Let's assume one general example. Let's here A has a 2 cross 3 dimension, and let's assume B has an 3 cross 2. So now you can see AB exists because this 3 is the same as this 2, and BA also exists. B BA also exists, and it has a dimension of 3 cross 3, and here it has dimension of 2 cross 2. So now you can see AB also exists and BA also exists, but this matrix A and B itself are not square matrices, because here the number of column and number of rows are different. So we cannot say the this condition A must be hold for the finding of BA. So option B is the wrong one. And let's move to the option B. Option B says if A and B are the symmetrics. Now here it is not the condition required for the finding of this BA matrix from this case. So we can say option B is the also wrong one. Wrong one. Now move on the option C. Option C says the only of A has many rows. Okay, here A has many rows as B has column. So now this is the case, because we have find out the in order to BA must exist, the here P and n r must be same. So here n is nothing but just a row of this A matrix, and p is number of column of B matrix. So that is they are saying in the option C. Again let look only if, sorry, here is if not of, only if A has many rows, A has many rows as B has column. So it is telling this condition number of uh, number of rows in the first matrix, it exactly same as number of column in the second matrix. Then and then the multiplication of BA and AB also both are exist. So option C is the correct one. Now also uh, go through the option D. Option D says only if A and B are the skew matrices. Now here again it is not the necessary condition. You can conclude from this example that this condition is also not necessary to exist this BA multiplication. So only the condition necessary is this C. So option C is the correct one. Okay, now let's solve question number 4. Question 4 says the inverse of a matrix. Okay, here we have a 3 cross 3 matrix, and they're asking about the inverse. So again, recall the formula. Inverse of matrix is just simply the 1 upon the determinant of this matrix and adjoint of this matrix. Here we are calling it A. So now first of all let's find the determinant of this 3 cross 3 matrix. So just we get this second term, we got minus 1, and here again minus 1. Now this first term and third term will 0. So now we only get the one term, which is the middle one. So here we get determinant equal to 1. So now let's put it here, 1 divided by 1. Now we have to find the adjoint of this matrix, which is 3 cross 3. Now here we don't need to find the whole adjoint. We just finding some element of this adjoint and compare it from the option which option is the correctly match with our findings. So first of all, let's find this element of this adjoint. So this element is corresponding to this 0. So we have to find the minors of this element. So first, just simply delete this first row and column. So I am finding the minors of this 1 element. So I have to just write the determinant of this 2 cross 2, which have entry 0, 1 and 0, 0. Now I have to find the determinant. I got 0. Simply I have to write 0 here. Now I have to multiply it with the sign factor to make it cofactor. So cofactor of 1 is just simply minus 1 raised to I plus j times a11. Here I and j are 1 and 1 respectively. So we got 1 and we got the determinant 0. So again we got 0. So we have to write 0 here. Now look at the option. Now option A will not correct one because here entry is given in the adjoint as a 1, sorry, in the inverse. So option A is the wrong. Now similarly option C is also wrong. Now look at this option B. The only remaining option are B and D. Now look at the this two matrices. Now the first row is same, so we don't need to find this the remaining element of this inverse. We have to just find this element because here it is 1 and here it is 0. If we find 0 here, then the option D is the correct inverse, and if we find 1, then the option B is the correct inverse. So let's find this element in this adjoint. So now remember, to getting the adjoint we have to take the transpose of this cofactor. Now this if we take in the transport, then the minors of this element will come here and it's make this element. So finding this element we have to find the minors of this a12. So let's find the minors of a12, which is located here, first row and second column. So just simply delete this first row and second column, write the remaining 2 cross 2 matrix. So here 0, 1, 1, 0, this matrix 0, 1 and 1, 0. Now find the determinant. We are getting minus 1, but we have to find the cofactor. So let's minus 1 raised to 1 plus 2, because here I and j are respectively 1 and 2 times minus 1. So again we get minus 1 multiplied with minus 1. Again we get positive 1. So now we find out this entry as 1. So now you can see option D is telling here in the inverse is 0, but we got the 1 as entry from this minus. So we can say option B is the correct inverse for this 3 cross 3 matrix. Now you can also check for this third entry for more clarity. Now here it is 1 and here it is 0. So again remember we have to take the transpose of this cofactor. So to finding this element in the adjoint we have to find the minus of this 0, and after taking the transpose we get this minus will be come to here. So let's find the minus of this a13 element to find this component, sorry, this element. So here let's delete this first row and this last column. So we end up with this again 2 cross 2 determinant 0, 0, 1, 0. Let's find the determinant. What we get 0. Now we have to find the cofactor, sorry, here 1 3 cofactor of this 1 3, it's again 0 because it is 0. Here determinant is 0, so we got 0. Now see option B is again the correct one and option D is the wrong because here the entry is 1 and we are getting 0. So only correct inverse for this matrix is B. So we have got the inverse by just simply finding these three entries. So option B is the correct inverse. Okay, now let's move to the next question. Okay, now question 5 says a system of equation represented by ax equal to 0. Okay, we have a system of equation which are represented by ax equal to 0. Here it is given that where x is a column vector, here x is a column vector in the form of variable and a is a containing coefficient. Here a is the coefficient matrix. So they are asking about the what is the condition that this coefficient matrix A should have satisfied such that the system has a non-trivial solutions. Now here you can we have on the right hand side we have 0 vector, so we can say the system is homogeneous system. Homogeneous system. So we know that the for any homogeneous system we have at least one solution, and which is simply just trivial, which is corresponding to all variable as 0. Let's assume here x, y, z are the variable. Then this is the always case for the homogeneous, and we call it trivial solution. But they are asking the condition for non-trivial solution. Now here, if this equation have this system have non-trivial solution, it is only possible if the determinant of this matrix is 0. If the determinant of A equal to 0, then we can say A has at least A has A has at least two row or column which are linearly dependent. Now this is the case, then we have to assume the general condition for any variable either x, y, z. So we have to assume any general number, and then according to that we are getting the value of this variable x and y, and they are non-zero, so we get a non-trivial solution. If this condition is hold, the determinant of A is 0, then we get the non-trivial solution for this homogeneous. So option C is the correctly describe the condition of A to getting these non-trivial solutions. You can also look by this way. If the determinant of any matrix is 0, then we can say that two rows are linearly dependent. Then we can at least make one row as 0 by some row operation, and we already have here right hand side we have 0. So now here maybe some number, let's call it A, B, C, D. Now we can see the rank of this matrix is always less than the order of this matrix, which is here we have assumed 3 cross 3. So here it may be possible the rank is 1 or 2, but it must be less than 3. And then the determinant will be 0. So rank must be less than 3. Now here we have three variable x, y, z. So the rank is less than the number of variable. Again we can say the system has infinitely many solutions, and they are non-zero solutions. So again we can say the A, which is a coefficient matrix, must be sorry, not non-singular, singular. Singular. Option B is the correct one, because here a non-singular means determinant equal to not equal to 0, but we need equal to 0. So matrix A must be singular. Sorry for that. Option C is the wrong one. Option B is the correct condition for this matrix A to get a non-trivial solutions. Okay, now let's move to the question number 6. Question 6 asking about the solution of this system. So first of all, let write in the matrix form. So here we have to write the coefficient matrix. Let's start with this first equation. Now here we have to write this column in the form of x and y. We have two variable here, x and y, but we got the three equation. So this system is over determinant. So on the right hand side we have to write here 8, 9 and 1. Let's form an augmented matrix, and let's write it here. We have 4, 6. On the right hand side we have 8, 7, 8, 9, 3, 2 and 1. Now all we have to do is just simply apply some row operation and reduce this matrix. So here look at the entries. Here we got 7 and here we got 8. Now look this first row and third row. If we add this third row, if I add this third row in the first one, then here I am getting 7. Here again I am getting 8. Now which is the exactly same as this row. So let's add this R2 in R1 and sorry R3. Let's add R3 in the R1 and it gives new R1. So after that, what we are getting? Just simply here 7, 8. Now here 9. Sorry, 8 plus 1 9. Now 7, 8, 9 as it is. The last row will also remain as it is. Now you can see this first and the second row are exactly same. We can apply one more row operation, which is R2 minus R1 will be new R2. So after that, what we are getting? Just simply first row again remain as it is. Now this second row will reduce to 0 because it is identical to the first one, and the last one also as it is. So now we have to we have reduced this third row. Now we have to find the we have to find the condition. Sorry, not condition, but the solution of this, not in terms of x and y, but just simply we have to tell either this system has solution or no solution. So here we can see this row 1 and row 3 are linearly independent because we cannot reduce it as in perfect this 0 0 form. So we can say they are linearly independent. So we got the rank of this matrix as 2 and the rank of this augmented matrix also as 2. So we can say the rank of this matrix and the whole as an augmented matrix is considering this last column is exactly the same and it is equal to 2. So the rank of this system has 2 and we also got the number of variable here is it is the exactly 2 x and y. So we have a unique solution for this three equation. So only one solution, or in the other word, unique solution for these three equation will exist. Okay, now let's solve question number 7. Question 7 says the eigenvalue of a matrix M are given as 15, 3 and 0, and here M is also given. Here M is a matrix of third order and it is a square matrix. So they are asking about the determinant of these 3 cross 3 matrix. Here we don't need to find the determinant of this matrix by expanding this. Here we just have to use the property. Simply we get the answer in the two step. We have to just multiply this 3 eigenvalue because here it is an 3 cross 3 and that's give the determinant of this matrix M. So here the eigenvalues are given and here one eigenvalue is 0. So the multiplication of this C number also 0 and it is nothing but the determinant. So we can say that the determinant of this matrix is 0. In the other word, M is singular matrix, singular matrix because we got the determinant equal to 0 and it is the necessary condition for the any matrix to become a singular. So the determinant is 0 for this matrix M. Okay, now let's solve question number 8. Question 8 again asking about the rank of this matrix and here it is an 3 cross 4 matrix. So here let's first of all write this matrix as it is. Now we have to apply some row operation to reduce this matrix so that we can easily find the rank. So here now again look, if I add this last row in the first one, so in here I am getting 6 and here I am getting 3 which is exactly same as this 3. Now here I am getting 1, it is not same as 4 and here 4 is also not same. So let's edit, we at least reduce this 2. So R1 plus R2 sorry R3 will gives new R1. So after that what we are getting here 6, 3, 1 and 4. Now here, to reduce the matrix, we don't have any fixed step. You can do by the any row operation. You can also do by your own row operation, which are different than I am doing. So now let's further do the operation row operation. Here let's subtract this first one from this second one, which is r2 minus r1 will give new r2. So now this first will remain as it is. Now here we got 0, again 0, 3, and here also 3. Now here 2, 1, 0, 1. Now we have to again apply some row operation. Okay, now what we have to do, we have to reduce this last row. So sorry, we can easily reduce this first one. First entry is 0 by multiplying this row with 3 and subtracting from this first one. So let's write it here. R1 minus 3 times R3 will give new R1. So after that, what we are getting here, we got 0. Here again, we got 0 again. Now here, 1 as it is. Now I have to multiply this line, this last row with minus 3. So here I am getting minus 3, plus 4 already there. So I am getting 1. Now here 0, 0, and this second row as it is, and third one is also as it is. So now you can see this row 2 and row 1 are same. In other words, they are linearly dependent. Row 1 and row 2 are linearly dependent. So we can reduce further by one more row operation by just multiplying this first row with minus 3 and adding in this second one. So again we get here all entries is 0 in the second row, and from that we can say that this matrix has two rows which are linearly independent, which are just this last one and this first one. So we find out the rank of this matrix, which is just simply the number of linearly independent row of this matrix, and here it is 2. So we can say that the rank of this matrix is simply just 2. Okay, now let's solve question number 9. Question 9 asking the determinant of this matrix. Here it is an 4 cross 4 matrix. Now if we expand this matrix, so we have to solve again this 3 cross 3 matrix. But here it is not required to expand it, because recall the property of this kind of matrix. What we call it? It's just we call it a lower triangular matrix. So now we got that this matrix is nothing but the simply the lower triangular, and we also know the properties of lower triangular and upper triangular. Let's write it here. Now here it is the property for any lower triangular or upper triangular, that the determinant of any matrix which is either lower triangular or upper triangular, it is just simply the multiplication of this diagonal element. Here it is given that entries are 1 1 1 in the diagonal. So now the order does not matter here. It is maybe 100 cross 100 or 1000 cross 1000. We have to just simply multiply this all diagonal element and we find the determinant. So let's find here. So here multiply this all 4 entries. Simply we get the one, and it is the determinant of this 4 cross 4 matrix. So simply option C is the correct one. Okay, now let's solve question 10. Here question 10 is asking about the eigenvalues of this 4 cross 4 matrix. Now here, if we go by our conventional method of finding the determinant and equate is equal to 0 and solve the characteristic equation, here it is in 4 cross 4 matrix, so it is too long and take more times. So what we have to do is just simply use the property. We have to use two property of eigenvalues, which are, first one is that the summation of these eigenvalue, here it is in 4 cross, so let's assume the it has a lambda 1, lambda 2 and lambda 4 as an eigenvalue. The sum of these four is nothing but the trace of this matrix. Let's call it matrix M. Now here we can find the trace easily by just simply adding this diagonal element. Here 0 plus 0 plus 0 plus 1, so we get trace of this matrix M is in 1. So now look at the option. The sum of this four value in the option A will give 0. So option A is the not correct set of eigenvalue for this 4 cross 4 matrix. Now again option B is also not correct one. Now option C gives the sum as 4. Again option C is not correct. Now the only option D remaining and it gives sum equal to 1. So we can easily say that option D is the correct set. Now also use the second property, which is the multiplication, for more clarity that the option D is the right one, equal to determinant of this matrix M. Now here it is in 4 cross 4 matrix. So how to find the determinant? We have to just decompose it into minus of 3 and solve for this 3 cross 3, and then we get the determinant of this matrix. Now here you can see this matrix has this first column has all entry as 0, and we know from the property of determinant, if any matrix A, sorry, any determinant has all 0 in the row, in any row or column, then the determinant in the output we get 0. So here we can say the determinant of this matrix is 0. So now multiply this number, we get 0. So again this second condition is also hold. First one is also hold for option D. So option D is the correct set of 4 eigenvalue for this matrix. So now we can easily solve within the fraction of second for the eigenvalue by this property. And that's it, we have done. And thanks for watching this video.